Hello, welcome to today's video, which in an alternative universe could have been part of my Prove It series. However, because this is a proof that we're expected to know for the further maths A-level exam, depending on what exam board and what modules you take, therefore it has become a tutorial video instead. Because today we're proving why the equation of a parabola looks the way it does, based on information given about a locus of points. Because of the presence of that word loci in the title here, it's worth noting that this is not to be confused with the general idea of a loci question that often gets asked as part of conic sections questions, because I will be having a separate video on that in the future. So therefore, if you're looking for advice with how to deal with those questions, go and have a look at that video instead, because this video is just focused on this very specific proof. But what do we need to know in order to be able to do this proof? Well, suspiciously in my previous videos on conic sections, I'd been rather vague about what a focus and a directrix were, other than saying that a focus was a point and a directrix was a line. Well, we're going to partially correct that issue today, because I'm going to explain a bit more about what a focus and a directrix mean when it comes to a parabola, specifically, because all the points on a parabola are defined as being equal distance away from both the focus and the directrix. So that is why the focus and directrix are important. It's also worth noting that this fact, though, is only true for a parabola. The focus and directrix have a slightly different relationship with the other conic sections curves, and that's something we will discuss in a future video. But for the moment, this is why a focus and directrix are important specifically for the parabola. Cool! So, with this information, we'll therefore be able to prove why a parabola has the equation it does, because we're going to look at proving that the locus of points are equidistant from a line with an equation x plus 10 equals 0, which by the way already means we know it's a vertical line because it's just got an x and no y involved, and the point 10, 0, which is labelled f suspiciously as if it's related to a focus. And we've got to prove that that locus of points forms a parabola. Cool. Things to note. I mean, first of all, it's always a good idea to draw diagrams. So to kick things off, we've got some axes drawn without a ruler, which is, me giving a terrible example to you. You should always draw diagrams with a ruler, preferably. But anyway, so we've got the vertical line, x plus 10 equals 0, which goes through the x-axis at minus 10. And then we've got the point 10, 0, which is there. Cool. So, with that in mind, some of you might be already looking at this question going, well, I already know the answer. Because if we look at the equation of the line that we've been given, that looks suspiciously like the equation of a directrix given to you in the form booklet for a parabola. And similarly, those coordinates look rather like the coordinates for a focus given for a parabola in the form booklet as well. And therefore, from that information, you might already be able to deduce that the equation of our parabola will end up being y squared equals 40x. And you would be correct about that. However, the question does say prove that the locus of points forms a parabola. And that's important because we've got to show that that is the equation based on the information we've been given here, rather than just knowing the directrix and the focus and just plugging into a formula. So, therefore, we are expecting the equation of the curve to end up looking something like this if I draw a parabola freehand. Not the best drawing in the world, but it will do, because then, in theory, we should be able to pick any point on this parabola, and what we're expecting to end up having happen is that the distance from that point to 10, 0, and the distance from that point to the line x plus 10 equals 0 should be the same as each other. Now, if you look at my diagram, they aren't the same as each other, and that's because I didn't draw a perfect parabola, but they should be the same. So, in order to do this proof, what we're going to do is we're going to define every point on the parabola as just the generic coordinates x, y, and then we're going to effectively find what the restrictions are on these coordinates x, y in order to meet these requirements given to us. The easiest starting point for this proof would be to begin by calculating the distance from xy to our directrix, because our directrix is a vertical line in this case, and therefore the shortest distance to it must be horizontal, because the shortest distance to anything is always a distance that's perpendicular to the line we are dealing with. So that's important because it means we just have to use x coordinates to be able to work out what the distance is. For instance, the distance from the line x plus 10 equals 0 to the y-axis would be a distance of 10 because of the fact we know the coordinates of the two vertical lines. One's at x equals 0, one of them's at x equals minus 10, effectively. And then to get from the y-axis to the point xy, well, just by looking at the x-coordinates, we can tell that's a horizontal distance of x. So therefore, already we know the horizontal distance is x plus 10 in total. So that's the distance from our point to the directrix. We now need to find the distance from the point to the focus, which is going to be a diagonal distance. But that's not a problem, because we've already dealt with that before in Maths A level. Of course, it's just effectively using Pythagoras with the horizontal and vertical distances to form the diagonal distance. The vertical distance, quite easy to do, because the y-coordinate of our point is y, the y-coordinate of the focus is 0, so that's a distance of y vertically. And then for the horizontal distance, we're going from an x-coordinate of x to an x-coordinate of 10, which could be a distance of x minus 10, going horizontally like that. Cool! So therefore, we know, using Pythagoras, that the distance from the point xy to the point 10, 0 will be the square root of x minus 10 all squared plus y squared. Nice! The rest of this proof is then just doing algebra. So, one thing I could do immediately to make our life a bit easier to deal with, I could square both sides to get rid of that square root. So if I do that, I end up with x plus 10 all squared equals x minus 10 squared plus y squared. Then multiply out the brackets. The brackets on the left-hand side of the equals would be x squared plus 20x plus 100. And then the x minus 10 all squared will come to x squared minus 20x plus 100 plus the y squared, which we've done nothing with. Interesting, you will therefore notice that straight away the x squareds are going to cancel out on both sides and the 100s are going to cancel out on both sides, meaning we're just left with 20x on the left hand side, and on the right hand side we have the minus 20x plus the y squared. And then what do you know? The final thing we've got left to do is add 20x onto both sides, and we've ended up with exactly the equation we're expecting to get. Y squared equals 40x. However, one final thing that it would be a good idea to do is to include a conclusion, because this is a proof, and therefore a good way of showing that this is indeed a parabola is to make the link between the equation we have and the general form of a parabola that we normally use in this conic sections chapter. So to do that, what I'm going to do is I'm going to basically factorize the 40x into being 4 lots of 10x, because then that means I can say, therefore, this is a parabola with a parameter of a equals 10. There you go. So we have done it. We've proven that the locus of points that are equal distance from a point on a line form a parabola curve. Of course, I was using numbers here. In the exam, they are happy to actually make you do a fully algebraic proof with just A's instead of numbers here, and that would be no more difficult as long as you didn't get put off by the fact that there were no numbers. Still a good idea to draw a diagram and go through effectively the same logic that we already went through. They can also make this a slightly different question by, instead of having a vertical line and a point on the x-axis, they could have a horizontal line and a point on the y-axis instead, or in reality a point anywhere they like, because then it's still going to be the same idea, but just instead of looking horizontally and diagonally, we're looking vertically and diagonally to calculate the respective distances to the directrix and the focus. Okay, hopefully you found this video useful and maybe even interesting, because it at least explains now why we care about a focus and a directrix, and what's so special about a parabola in comparison to the other conic sections curves. Okay, that will do us for today's video, and I shall see you in a future video. Goodbye.